Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to talk about what AI is and explore the difference between symbolic and statistical approaches.
It's a great topic because AI has just, exploded. It's moved from something you'd see in the movies right into our phones, our cars, everything.
Right, and we hear all these terms, chatbots, generative models. But I think for most people, the actual technical definition of what artificial intelligence is, it's still pretty fuzzy.
It is. People know it when they see it in action, but pinning it down is the real challenge.
Absolutely. So I think that's where we have to start. We have to kind of take that academic definition and just break it down into simple terms.
And at its core, AI is really about making rational decisions. The technical definition is that an AI is a system that tries to choose the best possible action it can take in any situation.
The best possible action. It's trying to be optimal.
Exactly. And researchers have a formal phrase for this goal. They say an AI tries to maximize expected utility.
Okay, that sounds like pure jargon. Let's unpack that.
Yeah, it does, but it's actually a fantastic way to understand the whole philosophy behind AI research.
So let's start with utility. What does that mean here?
Utility is just a score. It's how good or bad the outcome of an action is. If I choose to walk to a meeting, maybe the utility of getting some exercise is, say, +5.
And the utility of arriving on time is +10, so you're scoring the results.
You're just scoring the results. And then there's the expected part.
Right, because the world isn't certain.
Precisely. Early AI kind of assumed a world of perfect knowledge, like a game of chess where you know everything. But the real world is all about probability. Expected just means the AI has to weigh those utility scores by how likely they are to happen.
Okay, so if walking has a 90% chance of being great, but a 10% chance of a sudden thunderstorm?
And that thunderstorm gives you a -50 utility.
Then the AI has to factor that in. It's looking for the best average score over time.
Exactly. It's maximizing its average outcome in the long run.
That makes a lot of sense. But if the definition is that logical, why did the first few decades of AI research? Well, why did they hit so many walls?
It was because of this huge foundational assumption they made in the early days, the assumption of perfect knowledge.
What do you mean?
The first systems, they assumed they knew all the rules of the world. They assumed they knew the exact goal, the perfect utility function that the human wanted. The whole mindset was, I know the rules, I know the goal, now let me compute the one right answer.
Which is fine if you're in a lab or a very defined environment.
But it's completely inadequate for reality. It implies a level of certainty that just doesn't exist when you're dealing with people.
Because we humans are messy.
Exactly. And AI almost never knows exactly what we want. Our preferences are ambiguous. Sometimes they contradict each other. They're definitely not written down in a nice, clean equation.
So if I tell my AI assistant, help me be healthier, but also save money, those two things can be in direct conflict.
Right. The utility function itself is murky. And that realization, that shift, was massive for the field. It changed the entire paradigm.
So modern AI isn't about perfect calculation anymore. It's about operating with deep uncertainty, especially about what we want.
It moves from, I know the rules, to something more like, I have to figure out or learn what the human wants and then act cautiously because my understanding of their goal is probably flawed.
That's a huge shift in thinking.
It is, and it gave rise to all these new techniques, things like inverse reinforcement learning.
Okay, what's that?
Instead of the human just giving the AI the goal, the AI watches you. It observes the choices you make, the things you do, and it tries to reverse engineer the hidden reward function that would explain why you're doing them.
So it's trying to figure out what I must care about based on my actions.
It's trying to infer your values. And that changes everything. It turns the AI from a simple calculator into an observer, a modeler of human desire.
And is that why modern systems seem so cautious sometimes? They'll avoid doing something irreversible, or they'll ask, are you sure you want to do that?
That's a big part of it. When the expected utility is too close to call, maybe there's a huge potential payoff, but also a catastrophic risk, it hands control back to the human. It's acknowledging its own limits.
To make this a bit more concrete, there's a classic way of thinking about any AI system, right? the
Yeah.
agent model.
Yes, it's the perfect framework.
Hmm.
And the self-driving car is the best way to illustrate it. It breaks the system into 4 parts.
Okay, so first you have the agent. That's the AI itself, the brain, the software making the decision.
Right, the thing trying to maximize utility.
Yeah.
Then you have the environment. For the car, that's the road, the traffic, the weather, everything outside the agent.
And then you need a way to connect the two.
Which brings us to the sensors and the actuators.
The sensors are the AI's eyes and ears,
Mhm.
the cameras, the radar, all the data coming in.
And the actuators are its hands and feet, the steering wheel, the brakes, the way the agent acts on the environment. It's a constant loop. Sense, think, act.
And when researchers think about that agent, they see a gap, right, between what's perfect and what's real.
A huge gap. There's the ideal agent function. That's the perfect, unachievable recipe for what the agent should do in every single possible situation if it had infinite time and power.
And then there's the reality.
Then there's the agent program, the actual messy, limited code running on a real computer. And really, the entire history of AI is the story of trying to close that gap.
So all the different approaches, the successes, the failures, it's all about trying to write a better agent program.
Exactly. And that struggle led to 2 major competing philosophies, symbolic and statistical.
Okay, so before we get into that big conflict, let's just lay out the common ground. What are the essential ingredients that any intelligent system needs, no matter which philosophy it follows?
There are 4 big ones. The first, and maybe the most relevant one today, is understanding language, what we call NLP, how the AI reads and talks to us.
Makes sense. Second, you need a memory, a way of storing knowledge.
Right, knowledge representation. It has to organize what it learns so it can find it again. It's the difference between a messy pile of notes and a well-organized library.
Okay, so you have language and you have knowledge. What's third?
Reasoning. Automated reasoning. This is pure logic. If the system knows all humans need sleep, and it knows I am helping a human, it can deduce certain things from that.
It's step-by-step thinking.
Deductive, step-by-step processing. And the final ingredient, the one that really came to dominate, is learning from examples, machine learning.
This is where the AI improves just by seeing tons of data without a human having to write a new rule every time.
Exactly. And the whole philosophical split in AI history really comes down to which of those ingredients you think is most important.
So the symbolic camp, they focus on reasoning and logic.
They bet everything on knowledge representation and automated reasoning. They believed intelligence came from explicit rules.
And the statistical camp.
They staked it all on learning from examples. They thought intelligence was all about finding patterns in data.
All right, let's start at the beginning then. Act 1, Symbolic AI. This is also called GOFAI, right?
Right. Good old-fashioned AI. This was the dominant way of thinking from the 50s all the way through the 80s.
And the core idea, it was really ambitious.
Incredibly ambitious, and it's deeply rooted in, really, all of Western philosophy. The idea was, if we can just write down all the rules of thought in a formal language, a machine will be able to think.
So they saw intelligence as just manipulating symbols according to logical rules.
Precisely. The Lego analogy is perfect for this. They were trying to build a mind brick by brick, where every single brick was a perfect logical rule.
You can see the appeal. It feels so elegant and controllable.
Oh, absolutely. And they felt they had history on their side. The philosophical ancestor here is really Aristotle.
Way back in ancient Greece.
Yeah. In the 4th century BCE, he was the one who formalized deductive reasoning, the syllogism. If A is true and A implies B, then B must be true. Symbolic AI was basically the attempt to put Aristotle's logic on a computer.
And there were even earlier attempts to mechanize thought, right?
For sure. In the 14th century, a philosopher named Ramon Lull built these incredible reasoning machines. They were made of rotating wooden wheels with symbols on them. And you could turn the wheels to combine concepts and generate new ideas. It was that same spirit, trying to turn messy human thinking into a predictable, mechanical process.
It's funny that Alan Turing, who kind of set the stage for all of this, he actually predicted that learning would be the key.
He did, but the early researchers, they were so drawn to the clarity and control of formal logic that they went with the rule-based approach instead. It just felt more manageable than the chaos of learning from data.
So practically speaking, how did these symbolic AI systems work?
They needed 2 things we just mentioned. First was knowledge representation. This meant human experts had to sit down and painstakingly write down facts in a structured, formal way.
And these facts had to be totally explicit.
Totally. You couldn't just show the system a picture of a house. You had to type in facts like room A is connected to room B. Every single relationship had to be defined by a person.
Okay, so you have this database of facts. What then?
Then you need the engine to run it, which was automated reasoning. This was basically algorithms that would search through all those facts and rules to find a path to a goal.
So it's applying logic step by step to find a solution.
Exactly. We can think of it like a literal assistant. A symbolic AI is like a brilliant assistant who you've given this massive 1,000-page binder of rules.
And it follows those rules perfectly.
Perfectly and transparently. You can always look back and see exactly which rule made it take which action. But if it runs into a situation that's not in the binder,
It's completely lost.
it fails completely. It has zero ability to guess, to generalize, or to deal with anything ambiguous.
And that would turn out to be a huge problem. But in the beginning, in very structured worlds, it worked surprisingly well.
It really did. The robot Shaky at Stanford in 1971 is the classic example. It showed that symbolic reasoning could actually control a physical robot.
So what did Shaky do?
Shaky was a breakthrough because it used symbolic planning. It didn't just react to what its sensors saw. It used a planner called STRIPS.
STRIPS. That's an acronym for something.
Stanford Research Institute problem solver. You could give it a high-level goal, like go find that box and push it into the hallway.
And it would figure out the steps on its own.
Right. The STRIPS planner would work backward from the goal. It would say, okay, to push the box, I first need to be next to the box. To get there, I need to go down the corridor. It would generate this whole logical sequence of actions, turn, move, push, before it ever moved a single wheel.
That's pretty amazing for 1971.
It was a huge success, and it made researchers believe they could scale this up from moving boxes to doing really complex human tasks, which led to the era of expert systems.
So they tried to apply this to fields where the rules seemed really clear.
Exactly, like chemistry. Dendrol, which came out of Stanford in the late 60s, was a massive success. It helped chemists figure out the structure of complex molecules by applying strict chemical rules.
And it worked because chemistry is very rule-based.
It's clean, it's mathematical, but then emboldened by that, they tried to tackle a much messier field, medicine.
With a system called MYCIN in the 1970s.
Right. MyCIN was built to diagnose bacterial infections, and this is really where the symbolic approach started to show its cracks.
Because medicine isn't 100% certain, there's a lot of guesswork.
A lot. So MyCIN had to try and model that uncertainty. They created these certainty factors. A rule might say something like, if the patient has symptom Y, then conclude they have infection Z with, say, 80% confidence.
So they were trying to put a number on a doctor's hunch.
In a way, yes. And they had to sit down with doctors and painstakingly extract about 450 of these explicit weighted rules.
That sounds incredibly difficult.
It was. And that effort led directly to the first major reason for the AI winter. The knowledge bottleneck.
What was the bottleneck?
It was the slow, painful realization that you just couldn't write down all of human expertise. It's too slow, it's too expensive, and experts disagree with each other all the time.
And the rules themselves would be brittle.
Incredibly brittle. The second the system saw a patient with a slightly new symptom or a weird combination of factors that wasn't in one of the 450 rules, it just... It broke. It had no ability to generalize.
So that's one crisis. What was the other one?
Even if they could write down all the rules, they ran headfirst into an even bigger, more fundamental problem. The combinatorial explosion.
That sounds bad.
It's a mathematical brick wall. Symbolic systems work by searching through all the possible options to find the best one.
Trying option A, then option B, then C?
Right. Think about one of those little sliding tile puzzles. A simple 8 puzzle has about 181,000 possible states. A computer can search that in a split second. But if you just increase the size a little bit to a 15 puzzle, the number of possible states jumps to 10 trillion.
10 trillion, from 180,000.
10 trillion. It's an exponential growth. And that means adding just a little bit more complexity, a few more symptoms in a diagnosis, a few more objects in a room for a robot, makes the problem computationally impossible for any computer on Earth.
The search space just becomes too big to explore.
Exactly. And this mathematical reality just killed the optimism. The UK government put out the Lighthill Report in 1973, which basically said, these systems can't scale to real-world problems.
And that led to funding cuts.
Massive cuts. The field went into the first AI winter.
So the big takeaway from the symbolic era is that it was elegant, it was transparent, but it was just too brittle. It couldn't learn and it couldn't scale.
It couldn't handle the complexity and uncertainty of the real world. The field desperately needed a new approach, a way to build systems that could learn from all that chaos instead of just being told the rules.
Which brings us to Act 2, Statistical AI.
A complete philosophical pivot. The new idea was revolutionary, but simple.
Which was?
Intelligence doesn't come from human-written rules. It emerges from finding statistical patterns in huge amounts of data.
So instead of telling the machine a long definition of what a dog is,
you show it 1,000,000 pictures of dogs and let it figure out for itself the statistical patterns that define dogness.
Now, this idea of learning from data wasn't brand new, right? People had been working on things like neural networks for a while.
They had, but the approach never really took off because it was missing two critical ingredients, and those ingredients finally became abundant in the 90s and the 2000s.
Okay, what were they?
First, the data explosion. The internet, social media, cheap sensors. Suddenly, there was this massive amount of digitized data. Symbolic AI couldn't use that messy, real-world data. Statistical AI absolutely thrived on it.
It was the fuel it needed.
It was the fuel. And second, just raw computational power. These statistical models need to do billions of calculations. It was only when computers got fast enough and memory got cheap enough that these algorithms could actually run on a scale that mattered.
And the first ways of these statistical models, things like decision trees, they proved the concept was viable.
They did, but they still had a bit of a bottleneck. Human engineers still had to do what's called feature engineering.
Meaning you still had to tell the system what parts of the data to pay attention to.
Exactly. You had to tell it, look at the shape of the ears, or pay attention to these 3 economic numbers. It was still a bit manual.
So what broke that final barrier?
Deep learning. This was the moment everything changed. It brought back the old idea of neural networks, which had kind of been abandoned for decades.
Why were they abandoned?
There was a famous book in 1969 that proved that a simple single-layer neural network couldn't even solve very basic problems. But the key realization was that if you add more layers, if you make the network deep, you can.
But how do you train a network with dozens of layers? That seems incredibly complicated.
It is. And the technical breakthrough that made it possible was an algorithm called backpropagation.
Backpropagation.
It's the lifeblood of all modern AI. Basically, when the network makes a mistake, say it sees a picture of a dog but calls it a cat backpropagation, lets the system calculate exactly how much each of the millions of connections in the network contributed to that error.
So it figures out who to blame for the mistake.
It assigns blame, yes. And that error signal travels backward through the whole network. And it uses a bit of calculus to slightly tweak all those connections to make the error a little bit smaller next time.
And you just do that millions and millions of times.
Billions of times. And over time, the network refines its internal model of the world. And because it has so many layers, it can learn incredibly abstract patterns.
So the first layer might see raw pixels.
And the next layer learns to combine those into edges. The layer after that combines edges into shapes, like an eye or a nose. By the 10th layer, the network has automatically built up the concept of a human face.
And that's the key part. It does it automatically.
That is the crucial insight. Deep learning learns its own features. It completely eliminated the feature engineering bottleneck from earlier models, and it bypassed the knowledge bottleneck that killed symbolic AI.
It's incredible how that scales. And this all rests on some really core machine learning concepts, right? Like the bias-variance trade-off.
Absolutely. Every model has to manage this. High bias just means your model is too simple. It can't capture the complexity of the data. It underfits.
And high variance is the opposite.
It's the opposite. The model is too complex. It overfits. It basically just memorizes the training data, including all the random noise, and then it fails completely when it sees new data it hasn't seen before.
And deep learning somehow found the sweet spot.
It did. The architectures are complex enough to capture reality, so they have low bias, but they have built-in structures that prevent them from just memorizing everything, so they keep variance in check. They generalize really well.
And this also helps them overcome that other huge problem, the curse of dimensionality.
Which is really just another name for the combinatorial explosion that killed symbolic AI. When you have tons of features, the space of possibilities becomes unimaginably vast and empty.
It's impossible to search.
Right. But deep learning's trick is that it doesn't try to work in that huge high-dimensional space. It learns to compress all that information.
Oh.
It uses its layers to find a more compact, meaningful representation of the data. It learns the important shortcuts. So instead of dealing with 1,000,000 pixels, it learns to think in terms of a few hundred relevant concepts like fur, whiskers, and pointed ears.
And that power led to real-world breakthroughs. like AlphaGo.
AlphaGo is the big moment. The game of Go is vastly more complex than chess. You can't solve it with brute force symbolic search.
So how did AlphaGo win?
It combined both worlds. It used a deep neural network, the statistical part, to develop an intuition for which moves looked promising. And then it used that intuition to guide a more traditional symbolic style search.
So the learning part made the searching part smarter.
It pruned the search space dramatically. It showed that learning and planning could work together.
And now we see this power everywhere. In computer vision, that's better than human doctors at reading scans, in self-driving cars.
And of course, in generative AI, large language models are just massive statistical models that have learned the patterns of human language and knowledge so well that they can generate new, coherent, human-like text.
So it really seems like statistical AI solved all the problems that symbolic AI couldn't. It scales, it learns. Does that mean the old way, the logic-based approach, is just over? Is it dead?
You'd think so, but surprisingly, no. Symbolic AI is actually having a major comeback. A renaissance, really, but in a totally new role.
A supporting role.
Exactly. We've realized that for all its power, statistical learning has its own critical weaknesses. And those weaknesses are precisely where the old, logic-based methods are strongest.
Okay, let's lay that out. Statistical AI is great at what?
It's the champion of perception, pattern recognition, prediction, anything with messy, high-dimensional data. But its biggest weakness is that it's a black box.
It's not transparent.
Not at all. If a giant neural network makes a mistake, it's almost impossible to trace back why. You can't audit its reasoning.
Whereas symbolic AI, for all its brittleness, was the complete opposite.
Its greatest strength was its logic, its planning, its step-by-step reasoning. And because of that, its decisions are perfectly transparent and verifiable.
So Act 3 is the two of them getting back together.
It's the marriage of the two. We call it neuro-symbolic AI or sometimes agentic AI. It's the recognition that real intelligence isn't either rules or patterns. It's a seamless blend of both.
I like the analogy of a team. A modern AI system is like a team, where one member is the creative expert and the other is the project manager.
That's a perfect way to put it. The statistical part, like an LLM, is the creative expert. It can handle ambiguous human requests, generate novel ideas, understand context. It provides the fluency and intuition.
But then the symbolic part comes in as the project manager.
Yeah. It takes that raw, sometimes chaotic output from the LLM and it imposes structure. It breaks a big goal down into a logical, verifiable sequence of steps. It checks for consistency. It enforces hard safety rules.
So you get the power of one with the reliability of the other.
You do. You see this in safety-critical systems. An autonomous car might use a statistical model to predict where a pedestrian is likely to go.
That's the pattern recognition part.
But it absolutely must have a symbolic, rule-based system that enforces the hard constraint. You are never, ever allowed to hit a pedestrian. The statistical part provides the input, but the symbolic logic guarantees the safe action.
And this combination is becoming essential for more complex AI systems.
Yeah, it is. In multi-agent systems, the symbolic logic is often the coordinator. You might have one agent using an LLM to do research, but a separate planning agent uses purer logic to structure that research into a coherent plan. And a third agent uses logic to check the work for errors.
So the old GeoFAI, which was once a dead end, is now the essential scaffolding that keeps these powerful new statistical systems on track.
The great irony of the whole story is that in our quest for systems that could learn like humans, we realize that without the structure and transparency of good old-fashioned logic, we can't actually trust them. The ultimate intelligence, it turns out, is a hybrid.
It's fascinating. We've really come full circle from thinking it had to be one or the other to realizing the future is about blending them. Getting systems that can learn from the messiness of the world, but also apply strict logic to their own actions.
It really is. And it leaves you with a pretty interesting question to think about, I think. When you look at the best of what humans do, scientific discovery or making a really tough ethical choice, is our brilliance really in the intuitive pattern matching part of our brain? Or is it in the deliberate logical structure we impose on top of that intuition?
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.